What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. Sit as still as you can. Stop your hands. Slow your breathing. Hold yourself as motionless as a human body is able to be held. You are now traveling faster than any spacecraft our species has ever launched. Not a little faster. Right now, while you are doing nothing at all, you are moving through the universe at roughly 370 kilometers per second, more than 800,000 miles per hour. The fastest object we have ever built. A probe that fell toward the sun and used the star's gravity to whip itself forward, reached about half of that at its best moment, for minutes after decades of engineering. You are beating it. You are beating it in a chair. So here is the question. It sounds like something a child would ask, and it is one of the hardest things in modern cosmology to answer honestly. Which way? Not how fast. The question is direction. If you are moving at 370 kilometers per second, then there is a patch of sky your body is heading into, and an opposite patch you are leaving behind. And in principle, you should be able to point at it. Raise your arm. Aim. Most people reach for the same picture. Earth goes around the sun, so the instinct is to say the direction changes constantly, and that asking which way we are moving is like asking which way a horse on a carousel is facing. That instinct is not wrong, it is just very small. A second usually follows, from something half remembered about Einstein. Motion is relative. You only ever move with respect to something else, so the question has no real answer. That is not wrong either. It is one of the most thoroughly tested ideas we have, which is what makes the situation ahead so strange. Because despite that principle, and without violating it, cosmologists will tell you a specific speed and a specific direction. They will name a constellation. They will point. And the way they learn to point is the part almost nobody knows. The sky, it turns out, is not the same temperature all the way around. Fill the sky with the oldest light there is, the faint microwave glow left over from the era when the universe first became transparent, and measure its temperature in every direction. It comes out extraordinarily even. Wherever you look, the same faint cold, a little under 3 degrees above the coldest temperature that can exist. This is one of the most uniform things ever measured by human beings. Almost. Because when instruments got sensitive enough, a pattern surfaced underneath the evenness. One half of the sky is very slightly warmer than the other. Not warm. Nothing you could feel. The difference is about 1 part in 1,000. But it is there, it is not random, and it has a shape. One direction is the hottest point. The exact opposite direction is the coldest. Everything in between grades smoothly from one to the other, like a sphere lit from a single side. The sky has a hot side, and the hot side is not something out there. The hot side is us. That warm patch is the direction you are moving. Your motion, and the motion of the planet under you, and the motion of the star that planet orbits, all of it stacked together, is written into the temperature of the oldest light in existence, as a faint smear across the sky, pointing the way you are going. You have been leaving a mark on the universe your entire life. It is a temperature, and it points at Leo. If the idea that your own movement is recorded in the light from the beginning of time is the kind of thing you want more of, subscribing is a small way to help me make the next documentary. Because that answer, satisfying as it feels, immediately opens a much harder problem. If motion is relative, if there is genuinely no such thing as absolute movement, then how can a warm patch of sky tell you anything at all? What exactly are we moving with respect to? And why should a bath of ancient photons get to be the thing that decides? To take that seriously, we have to go back to the ship. There is a passage written in the early 1600s that is still, 4 centuries later, the clearest explanation of relative motion anyone has produced. Galileo asks you to imagine yourself below deck on a large ship, in a cabin with no windows. With you are some flies, a bowl of water with fish in it, and a bottle set up to drip water into a container below. While the ship sits at anchor, you watch everything carefully. The flies move around the cabin in all directions. The fish swim wherever they like. The drips fall straight into the container. You throw an object to a friend, and it takes the same effort to throw it toward the front of the ship as toward the back. You jump, and you land where you started. Now the ship sets sail. It moves steadily, smoothly, without accelerating, without turning, without rolling. Nothing changes. The flies do not pile up against the back wall. The fish do not have to swim harder toward the bow. The drips still fall straight down into the container, even though the container has moved a considerable distance while each drop was in the air. You jump, and you still land where you started, even though the deck beneath you traveled several meters while your feet were off it. You throw the object, and it takes exactly the same effort in either direction. The point Galileo is making is not that motion is hard to detect. The point is far stronger than that. The point is that no experiment you can perform inside that cabin, none, not one, will tell you whether you are moving or at rest. The behavior of everything inside is identical either way. Not similar, identical. Open the window and you can see the shore go past, and then you know. But that only tells you how you are moving with respect to the shore. Take the shore away, put the ship in the open ocean at night, and the question loses its meaning again. Are you moving, or is the water moving past you? There is no fact of the matter. There is only the relationship. 3 centuries later, Einstein took that idea and did something more radical with it. Galileo said the laws of mechanics look the same for anyone moving steadily. Einstein said, all the laws do, including the laws governing light, and then followed that through to its consequences. And the consequences reshaped space and time themselves. But the core survived unchanged, and it is the piece we need here. There is no experiment, anywhere, that reveals absolute motion. There is no cosmic shore. Every velocity is a velocity with respect to something you have to name. So hold that firmly, because it is true, and because everything that follows has to be consistent with it. And now hold the other thing, which is also true. There is a warm patch of sky. These two facts feel like they cannot both stand. If no experiment can reveal absolute motion, then measuring the sky's temperature is an experiment, and it appears to be revealing exactly that. Something has to give. Nothing gives. And understanding why nothing gives is the first real turn in this story. Go back to the ship. but change one detail. Do not open a window. Instead, fill the ocean with fog. Now the ship moves through the fog, and suddenly there is something you can measure from inside, if you can reach out into it. The fog piles up slightly against the front. It thins slightly behind. You have not discovered absolute motion. You have discovered your motion with respect to the fog. The fog is a thing. It is made of stuff. It has its own state of motion, and you can compare yourself to it. That is what the ancient light is. It is not a frame built into the laws of physics. It is not a cosmic shore. It is a substance, an enormous, thin, universe-filling gas of photons that has been traveling since the universe was about 380,000 years old. And like any substance, it has a state of motion. And like any substance, you can move with respect to it. Move toward it, and the light you meet arrives with its waves crowded slightly closer together. Move away, and the waves stretch slightly apart. You already know this effect because you have heard it. An ambulance approaches, and its siren sounds high. It passes and drops to a lower pitch. The siren itself never changed. What changed was your relationship to the arriving sound waves. Approaching, you meet the waves more often, and more often means higher pitch. Receding, you meet them less often, and less often means lower pitch. Light does the same thing. Crowd the waves, and the light shifts toward the blue end and carries slightly more energy. Stretch them, and it shifts toward the red and carries slightly less. Now apply that to a bath of light that surrounds you completely. Point yourself in some direction and start moving. The light coming from ahead of you gets slightly crowded, slightly bluer, slightly more energetic. Since the temperature of that light is just a way of describing its energy, ahead of you the light now reads as very slightly hotter, and behind you the reverse, stretched, redder, cooler. You have made the sky lopsided by moving through it. That lopsidedness has a name. It is called a dipole, which simply means a pattern with two poles, one maximum and one minimum on exactly opposite sides. A bar magnet has a dipole. So does a sphere lit from one direction. And so does the temperature of the oldest light in the universe, as seen by anyone who is moving. So the warm patch is not telling you that you have an absolute velocity. It is telling you your velocity with respect to that light. That is a real, specific, physically meaningful comparison, and it is exactly as legitimate as measuring your speed with respect to a road. It just happens that this particular road is the most universal reference object available, because that light fills everything and reaches everyone. Relativity is untouched. We simply found the largest thing available and compared ourselves to it, which raises an obvious next question, and it is a fair one. How would you actually measure something as delicate as 1 part in 1,000 across the whole sky, when the sky is also full of a galaxy, and the instrument is sitting on a warm, glowing, atmosphere-wrapped planet? The short answer is that for a long time, we could not. The microwave background was discovered by accident in the mid-1960s by 2 radio astronomers who spent months trying to eliminate what they assumed was a fault in their equipment. They cooled their receiver, they checked their wiring, they evicted a pair of pigeons from the antenna, and cleaned out what the birds had left behind. The hiss remained. From every direction they pointed, day and night, season after season. They had found the afterglow of the early universe by trying and failing to get rid of it. But finding that the hiss exists and measuring a 1 part in 1,000 asymmetry across it are separated by an enormous gulf of engineering. Early attempts flew detectors on high-altitude balloons and on a converted spy plane, lifting instruments above as much of the atmosphere as possible. Those experiments saw hints of an asymmetry through the 1970s. The hints were real, but they were ragged, and interpreting them meant subtracting the glow of our own galaxy from data that was noisy to begin with. The clean answer required leaving the atmosphere entirely. A satellite launched at the end of 1989 carried an instrument designed to do one thing extremely well. It carried 2 horns pointed at different patches of sky, and it did not measure the temperature of either one. It measured only the difference between them, over and over, as the satellite spun and orbited and slowly swept its pair of horns across the entire sky. Measuring a difference directly is far more precise than measuring 2 large numbers and subtracting, in the same way that a balance scale can detect a tiny weight difference between 2 objects far more reliably than weighing each one separately and comparing. Within a year, it had mapped the dipole with real precision. The sky was warmest toward the constellation Leo and coolest toward Aquarius, and the size of the asymmetry corresponded to a motion of a few hundred kilometers per second. Later missions sharpened it further. The figure settled at about 370 kilometers per second for the solar system's motion with respect to that ancient light. So we have an answer to the question we started with. You are moving toward Leo at 370 kilometers per second with respect to the oldest light in the universe. And that answer is correct, and it is also the least interesting version of the truth, because it hides everything underneath. That single number is not one motion. It is a stack of motions, layered on top of each other, each one a different story about a different structure, most of them far larger than the one before. Pulling that stack apart is where this gets genuinely strange. Start with the motion you already know. Earth goes around the sun at about 30 kilometers per second. That is a real contribution, and it does exactly what your first instinct said it would. It changes direction constantly. In one part of the year, it adds to our motion toward Leo, and half a year later it subtracts. Astronomers can see this in the data as a small annual wobble in the dipole, and it is genuinely useful because a signal that varies in a known way over a known period is a signal you can trust. The Earth's orbit acts as a calibration. We know exactly how fast the planet goes around the star. So when the dipole shifts by precisely that amount on precisely that schedule, it confirms that the whole measurement is behaving the way the physics says it should. But 30 is small compared to 370. Peel it off, and almost everything remains. Next layer. The sun is not sitting still either. It is orbiting the center of the Milky Way, carrying the entire solar system with it, at somewhere around 230 kilometers per second. That is a very large number, and it is worth pausing on what it means. In the time it takes you to read this sentence, the sun and everything bound to it has moved a distance greater than the diameter of the Earth, several times over, and yet this motion is so smooth and the galaxy so vast that it takes something like 230 million years to complete a single circuit. The last time the Sun was in this part of its orbit, the first dinosaurs were appearing. It has gone around perhaps 20 times since the Sun formed. That layer is large, but it points in a direction set by the geometry of our galaxy, and it is not pointing at Leo either. Peel it off, and something still remains. Now the object doing the moving is the Milky Way itself, and the story changes character. Because a galaxy is not a thing you can push. To move an entire galaxy, you need gravity. And to have gravity on that scale, you need mass. And mass on that scale means other galaxies, in enormous numbers, arranged in specific places. Which means the remaining motion is not really about us at all. It is a measurement of what surrounds us. Our velocity has become a probe of the structure of the universe. And when you finally strip away the local layers and ask what the Milky Way and its immediate companions are doing, you get a number that is larger than any of the individual pieces underneath it. The local group, the small gravitationally bound family of galaxies that includes ours and Andromeda, and a few dozen smaller members, is moving at roughly 600 kilometers per second with respect to the ancient light. 600, and nothing nearby explains it. That is the problem that occupied a generation of astronomers, and the search for what was pulling us is one of the strangest detective stories in 20th century science, partly because the suspect turned out to be hidden behind the one obstacle we can never move. We live inside the thing we are trying to see past. The Milky Way is a flattened disk, and we are inside that disk, roughly halfway out from the center, embedded in the plane. Which means that when we look outward at the universe, we look through our own galaxy in most directions. Toward the poles of the disk, above and below, the view is fairly clear. But along the plane, in the band of sky we call the Milky Way, when we see it stretched overhead on a dark night, the view is blocked. Stars in front of stars, gas, and above all dust, in vast quantities, absorbing and scattering visible light. Astronomers call that blocked band the zone of avoidance, because for a long time it appeared that galaxies simply avoided it. Maps of the sky drawn in the early 20th century showed galaxies scattered everywhere except in a broad stripe across the middle, where there were almost none. It looked like a real feature of the universe. It was not. It was a curtain. Picture standing in the middle of a large room at night, holding a lantern at chest height. The lantern lets you see the room, but it also ruins your night vision in a band all around you. You can see the ceiling clearly and the floor clearly. Everything at your own eye level is washed out. Now try to work out the shape of the building you are in. That is our situation, and roughly a fifth of the entire sky sits behind that curtain. So through the 1970s and 80s, astronomers had a measurement and no explanation. The local group was moving at 600 kilometers per second toward a direction that lay uncomfortably close to the plane of our own galaxy. Something enormous was pulling, and it was sitting almost exactly where we cannot look. The way forward was not to see the thing, it was to measure the pulling. Here is the idea. and it is one of the more elegant pieces of reasoning in observational astronomy. The universe is expanding, which means that on average, every distant galaxy is receding from us, and the further away it is, the faster it recedes. That relationship is smooth and predictable. So if you know how far away a galaxy is, you can predict how fast it should appear to be moving away. Then you measure how fast it is actually moving. The difference between the two, between the recession the expansion predicts and the recession you observe, is that galaxy's own motion through space, its motion on top of the general expansion. Astronomers call it peculiar velocity, using peculiar in its older sense, meaning belonging to itself rather than strange. Think of leaves on a slow river. The water carries everything downstream at a steady rate, and if leaves only drifted, they would all keep their spacing perfectly. But some leaves also get pushed sideways by eddies, or drawn toward a swirl. Watch long enough and you can map the currents you cannot see by tracking how the leaves depart from the pure drift. Do this for one galaxy and you learn very little. Do it for hundreds of galaxies spread across the sky, and something remarkable emerges. You get a flow map. You can see, region by region, which way matter is being drawn, and where the drawing converges. The difficulty is that the whole method depends on knowing distances, and distance is the oldest and hardest problem in astronomy. A faint galaxy might be small and close, or large and far, and nothing about its appearance alone settles it. The breakthrough came from noticing that galaxies are not arbitrary. In the late 1970s, astronomers found that the speed at which a spiral galaxy rotates is tightly linked to how much light it actually emits. Faster spin means a heavier galaxy, and a heavier galaxy is genuinely brighter. This matters enormously, because rotation speed can be measured without knowing the distance at all. You measure how much the galaxy's light is smeared by its own spinning, one edge coming toward you, the other going away. So the chain runs like this. Measure the spin. The spin tells you the true brightness. Compare the true brightness to how bright the galaxy actually looks from here. Something that is genuinely bright, but appears faint, must be far away, and the amount of faintness tells you how far. A similar relationship was later found for elliptical galaxies, using the internal motions of their stars. Now you have distances for hundreds of galaxies. Now you can compute peculiar velocities. Now you can build the map. A group of 7 astronomers set out to do exactly that during the 1980s, working with elliptical galaxies across the whole sky. They came to be known simply as the 7 Samurai, and what they found was not a gentle drift. Our galaxy was not merely falling toward the nearest large cluster. Everything in a huge region, including the nearest large cluster itself, was streaming together in the same broad direction, toward a point beyond it all, close to the plane of the Milky Way and hidden behind the dust. They gave the unseen source a name that has stuck ever since: the Great Attractor. The name is dramatic, and it has caused a certain amount of confusion, so it is worth being careful about what it actually refers to. The Great Attractor is not an object. It is not a giant black hole, and it is not a mysterious body of unknown physics, despite how the phrase gets used. It is a region. It is a place where the density of ordinary matter, galaxies and clusters of galaxies, and the dark matter associated with them is high enough that the surrounding volume of the universe is being drawn toward it. The mystery was never what kind of exotic thing it was. The mystery was what was there, because we could not look. Slowly, we found ways around the curtain. Dust blocks visible light effectively, but it is far less effective against longer wavelengths. Infrared light passes through much more of it. Radio waves pass through, almost as if it were not there. Neutral hydrogen gas, which fills galaxies in enormous quantities, emits at a specific radio wavelength of about 21 centimeters, and that emission sails through the dust of our own galaxy, essentially unimpeded. X-ray telescopes offered another route, because the hot gas that fills large galaxy clusters glows in X-rays, and a cluster hiding behind the Milky Way still announces itself that way. So astronomers began surveying the zone of avoidance with instruments that did not care about dust, and the empty stripe began filling in. What emerged was a massive concentration of galaxies centered roughly 250 million light-years away, in the direction of the constellations Norma and Centaurus. At its heart sits a rich cluster that had been catalogued but poorly understood, because much of it lies behind the worst of the obscuration. Around it, other clusters and groups, arranged in a broad concentration of mass. The Great Attractor had a location and a census, and then the story turned again, because when astronomers looked past it, they found that the Great Attractor is not the end of the pull. Further out, at something like 650 million light-years, roughly 2.5 times more distant, sits a far larger concentration, named after the astronomer Harlow Shapley. The Shapley concentration is the densest collection of galaxy clusters known in our region of the universe. It contains many rich clusters packed into a relatively small volume, and its total mass dwarfs the Great Attractor region. Being much further away, its pull on us is weaker than its size alone would suggest, because gravity weakens with distance. But it is not negligible. Current analyses suggest that a substantial portion of the local group's motion, quite possibly the larger portion, traces to the Shapley concentration and the broader distribution of mass beyond the Great Attractor, rather than to the Great Attractor alone. So the picture inverted. For a while, the Great Attractor looked like the destination. Now, it looks more like a station on the way. We are not falling toward one hidden object. We are falling down a long gradient in the density of the universe, and the Great Attractor is a prominent feature along that slope, rather than the bottom of it. And there is a further honest complication, which is that the sum has never fully closed. Different surveys, using different distance methods and reaching different depths, have historically disagreed about how much of our motion is accounted for by the mass we can identify. Some analyses find the local structures sufficient. Others find a residual, a portion of the flow that seems to require mass at distances so great that it becomes difficult to explain within the standard picture. That disagreement has narrowed over the decades as surveys have deepened, but describing it as fully settled would overstate the case. What is not in dispute is the direction and the fact of the flow. We are moving. The direction points into a region that was hidden and is now partly mapped. The pull comes from ordinary matter arranged in enormous structures, obeying gravity exactly as expected. But there is something deeper hiding in this method, and it took another 30 years to be recognized. Because if you can map the flow, you are no longer just explaining our velocity. You are being handed a completely different way of answering the question of where we live. Ask where you live, and you will probably answer with nested containers. A house, on a street, in a town, in a region, in a country. Each container is defined by a boundary drawn on a map. The boundary is the primary thing, and you are inside it. Astronomy did the same for a long time. The solar system sits inside the Milky Way. The Milky Way sits inside the local group. The local group sits near the edge of a large collection of galaxies, centered on the Virgo cluster, which was called the local supercluster. Each container defined by where things are. But there is another way to describe where you live, and anyone who has looked at a river system already understands it. Rain falls on a hillside. Some of it flows one way and eventually reaches one sea. Rain falling a short distance away, on the other side of a ridge, flows the opposite way and reaches a different sea. The two raindrops might land within arm's reach of each other, but they belong to different watersheds, because a watershed is not defined by where the water is. It is defined by where the water goes. This is a more revealing description than a boundary on a map, because it encodes the shape of the land. Tell me which watershed a place belongs to, and you have told me something about the terrain, the slopes, the direction of everything downhill. In 2014, a group of astronomers applied exactly this logic to the universe. They took the largest available catalog of galaxy distances and peculiar velocities, many thousands of galaxies, and instead of asking where the galaxies were clustered, they asked which way each one was flowing. Then they looked for the surfaces where the flow divides. On one side of the surface, galaxies stream one way. On the other side, they stream the other way. That dividing surface is a cosmic watershed boundary, and everything inside it belongs to a single basin of flow. Our basin turned out to be far larger than anyone had drawn before. It spans something like 500 million light-years and contains on the order of 100,000 galaxies the size of ours. The Virgo cluster, which used to be the center of our supercluster, turned out to be a modest feature within it. The Great Attractor region turned out to sit at the basin's focus, the point toward which the interior flow converges. They named it Laniakea, from Hawaiian words meaning immense heaven. And here is the part that matters, the part that reframes the whole question. Under this definition, our supercluster is not a lump of matter with edges. It is a flow pattern. Its boundary is not a wall. It is a ridgeline, a place where the pull from one side gives way to the pull from another. Nothing physically separates Laniakea from its neighbors. If you traveled to the boundary, you would notice nothing at all. It is defined entirely by which way things are going. This also means Laniakea is not permanent, and the astronomers who mapped it were explicit about this. The universe is expanding, and that expansion is accelerating. And one consequence of accelerating expansion is that structures which are not already gravitationally bound will eventually stop assembling and begin to separate. Laniakea is not bound. It is not going to collapse into one enormous object. It is a pattern in a flow, and over a long enough span of time, the accelerating expansion will pull that pattern apart, faster than gravity can gather it. We are not falling into anything. We are falling towards something that we will not reach. That is a genuinely strange thing to know about your own address, and it is worth being clear about which parts of it are directly observed and which are inference. The peculiar velocities are measured, though every distance measurement carries real uncertainty, and those uncertainties grow with distance. The overall pattern of flow toward the Great Attractor region is robust and has been confirmed by multiple independent methods. The specific boundary of Laniakea, however, depends on how the flow field is reconstructed from a finite and uneven sample of galaxies, and different reconstruction methods draw the surface somewhat differently. Later work using deeper catalogs has suggested that our basin may in fact be a lobe of something larger still, drawn toward Shapley, which would make Laniakea itself a subdivision rather than a whole. That question remains open. What is not open is the underlying method, or the fact that describing our place by flow, rather than position, revealed structure that position alone had concealed. So we now have a genuine answer to the question we started with, and it is layered rather than simple. You are moving because Earth orbits the Sun. The Sun orbits the galaxy. The galaxy moves within its local family. That family is falling down a gradient in the density of the universe, toward a region long hidden behind our own galactic dust, and beyond it, toward a greater concentration further out. Add all of it together, and it comes to about 370 kilometers per second, pointed at Leo, written permanently into the temperature of the oldest light there is. That should be the ending. The question is answered. The layers are separated. The mechanism is understood. Except that in the last few years, a different way of measuring the same thing has started returning a different answer, and nobody has been able to make the two agree. Everything so far rests on one assumption, and it has been sitting quietly underneath the whole argument. We assumed that the warm patch in the ancient light is caused entirely by our motion. That is why we could turn a temperature difference into a velocity. Take away that assumption, and the number means something else. It is a reasonable assumption. A dipole is exactly what motion produces. The direction is sensible. The amplitude implies a speed that fits with everything we know about the gravitational pull of nearby structures. But reasonable is not the same as tested, and for a long time, nobody had a way to test it independently, because the ancient light gives you one measurement, and one measurement cannot check itself. Two astronomers proposed a solution in the mid-1980s, and the idea is beautifully simple. If you are genuinely moving through the universe, the ancient light is not the only thing that should look lopsided. Everything should. Count the distant galaxies. If the universe is the same in all directions on large scales, and you are moving, then you should see slightly more objects ahead of you than behind you. Measure that imbalance, and you have measured your velocity a second time, by a completely different route. Two separate effects push in the same direction, and both are worth understanding, because together, they are what makes the test sharp enough to matter. The first is aberration, and you have experienced it every time you have run through falling rain. Rain falls straight down. Stand still with an umbrella directly overhead, and you stay dry. Now run. The rain now seems to come at you from ahead, at an angle, and you have to tilt the umbrella forward. The rain did not change. Your motion through it changed the angle at which it arrives. Light does the same thing. Move through the universe, and the apparent positions of distant objects shift very slightly toward the direction you are traveling. Everything crowds forward a little, so the sky ahead of you holds slightly more objects per patch than the sky behind. The second effect is about brightness. Objects ahead of you have their light shifted toward the blue and boosted in energy, exactly as we saw with the ancient light. So they appear slightly brighter than they otherwise would. Objects behind you appear slightly dimmer. That matters more than it sounds, because every survey has a limit. There is a faintness below which an object simply does not register, and near that limit sit an enormous number of objects, only just too faint to make the cut. Brighten everything ahead of you by a fraction of a percent, and some of those marginal objects cross the threshold and get counted. Dim everything behind you and some drop out. Imagine a crowd in fog, at the distance where figures are just barely resolvable. Improve the visibility slightly in one direction, and the number of people you can count in that direction jumps. Not because more people arrived, but because the edge of detectability moved outward. The steeper the pile-up of objects at the limit, the bigger the effect. Put aberration and brightness boosting together, and you get a predicted imbalance in the number of distant sources. And crucially, you can calculate exactly how big it should be for a given velocity. It is not a vague expectation. It is a specific number. So the test is clean. Take the velocity implied by the warm patch in the ancient light. Predict the source count imbalance. Then go and count. There is one requirement, and it is strict. The sources have to be far enough away that local structure does not contaminate the count. If you count nearby galaxies, you will mostly measure the lumpiness of our own neighborhood, the Virgo cluster and the Great Attractor region, and everything else we have been discussing. You need objects so distant that they sample the universe at a scale where it is supposed to be smooth. Quasars are ideal for this. A quasar is the blazingly bright core of a galaxy whose central black hole is actively feeding, and it can outshine everything else in its galaxy combined. That brightness makes them visible across enormous distances, which means a catalog of quasars samples a genuinely vast volume, far beyond any local structure. For decades, there were not enough of them, and the radio surveys that offered an alternative were not quite deep enough either. Then, infrared sky surveys changed the situation. A space telescope that mapped the entire sky in infrared produced a catalog from which more than 1 million quasars could be identified with reasonable confidence. In 2021, a team led by Nathan Seacrest performed the test with roughly 1.36 million quasars. The direction came out right. The quasar dipole pointed close to the direction of the warm patch in the ancient light, which is itself an important result, because a wrong direction would have suggested the whole method was broken. The amplitude did not come out right. It came out more than twice as large as predicted. Their reported significance for rejecting the purely motion-based interpretation was a probability of about 5 in 10 million, which corresponds to roughly 4.9 standard deviations. A follow-up analysis combining the infrared quasars with a radio survey found the dipole about 2.7 times larger than expected, at a significance of about 5.7 standard deviations. in a field where 3 standard deviations is interesting, and 5 is conventionally treated as the threshold for taking a result seriously, those are not numbers that can be waved away. So we have a genuine conflict. 2 independent measurements of the same quantity, our motion, disagree by roughly a factor of 2, in a direction where they agree. Now, what does that actually mean? This is where discipline matters, because there is a version of this story that gets told badly, and the bad version claims that cosmology is collapsing, or that we have found we are at the center of the universe. Neither claim follows. Let us walk through the possibilities honestly. The first possibility, and the one most working astronomers still consider most likely, is that something in the counting is subtly wrong. Counting quasars sounds simple and is not. You are identifying them from infrared colors, and that identification is imperfect. Some genuine quasars get missed. Some other objects get wrongly included, particularly stars in our own galaxy, which are distributed in a way that is anything but uniform across the sky. The survey's sensitivity is not perfectly even across the whole sky either, because of how the telescope scanned and how much of each region it covered. Dust in our own galaxy affects the infrared less than it affects visible light, but not by nothing. And the zone of avoidance, the same curtain that hid the Great Attractor, cuts a band through any all-sky catalog, forcing you to mask a large region and infer what would have been there. Any one of these, if it varies smoothly across the sky, can imprint a false dipole on your counts. The teams involved have worked hard on all of these. They mask the galactic plane generously. They apply cuts to remove likely stellar contaminants. They test whether the result survives when the analysis choices are varied. Independent groups have reanalyzed the same data with different statistical frameworks, including Bayesian approaches, and have generally recovered an excess, though the exact significance shifts depending on the method and the assumptions. But the honest position is that this is a measurement where the signal is a small imbalance in counts. And small imbalances are exactly where systematic errors live. The excess has survived a lot of scrutiny. That is not the same as being immune to it. The second possibility is more interesting, and it concerns not the counting, but the sources themselves. The prediction of the imbalance depends on properties of the population you are counting. Specifically, it depends on how the number of sources changes as you go fainter, and on how their brightness changes with wavelength. Both of those enter the calculation directly. If those properties are not what has been assumed, the predicted amplitude changes. There is a further subtlety. Quasars are not standing still and unchanging. They live at a range of distances, which means we are seeing them at a range of times in cosmic history. And quasars were more common and more active in the past than they are now. If the population's properties change with distance in ways that are not fully captured, the predicted signal shifts. Several papers have argued that accounting for these effects more carefully reduces the tension, though generally not to zero. Others have argued the corrections are small. This is an active and genuinely unresolved argument in the literature, and it is not the kind of argument that gets settled by rhetoric. It gets settled by better data. The third possibility is the one that gets the headlines, and it deserves to be stated precisely rather than dramatically. The prediction assumes the cosmological principle, which is the assumption that on sufficiently large scales, the universe looks the same everywhere and in every direction. That assumption is not decorative. It is the foundation on which the standard model of cosmology is built. It is why we can write down relatively simple equations for the universe as a whole. If the quasar-dipole excess is real, and not a systematic, and not an artifact of population modeling, then one way to explain it is that the distant universe is genuinely not distributed as uniformly as assumed. There would be a real excess of sources in one direction that is not caused by our motion at all, but by an actual asymmetry in how matter is laid out on scales far larger than any structure we have mapped. That would be a serious problem, not because it would make cosmology wrong in some sweeping sense, but because it would mean the simplifying assumption underneath many standard results is not quite right, and a great deal of careful work would need to be revisited. It is worth being clear about what this would not mean. It would not mean we are at the center of the universe. It would not mean the expansion is fake or the ancient light is misunderstood. And it would not mean that the physics we have been describing throughout this documentary, the Doppler effect, the dipole, the gravitational pull of the Great Attractor region, is wrong. All of that is measured and secure. What would be in question is a specific assumption about uniformity on the very largest scales. There is also a fourth possibility that sits underneath the other three, which is simply that the two measurements are probing different things, and the comparison is less direct than it looks. The warm patch in the ancient light comes to us from one surface, at one moment in cosmic history. The quasar counts come from an enormous depth of space and time, stacked together. Whether these two are guaranteed to give the identical answer under all circumstances is itself a question that has received real theoretical attention, and the answer is more subtle than a simple yes. What no one has done is make the discrepancy disappear. That is where it sits. It has been checked, reanalyzed, argued over, tested with additional catalogs, and it has neither collapsed under scrutiny nor been confirmed beyond dispute. It is a live problem, and new all-sky surveys now coming online will have far more sources and far better control of the systematics, which means this is a question likely to be resolved rather than one destined to sit open forever. So we should return to where we started and say clearly what we know and what we do not. We know the sky has a hot side. That is a direct measurement, made repeatedly by multiple instruments, with the pattern of a dipole and the direction toward Leo. That is not in question. We know that motion produces exactly such a pattern, by a mechanism, the Doppler effect, that we understand thoroughly and can demonstrate in a laboratory. We know that our galaxy sits within a flow, because we have measured the peculiar velocities of hundreds of galaxies by independent means and mapped the currents. We know that flow points toward a region that was hidden behind the dust of our own galaxy and has since been partly surveyed in infrared and radio and X-rays. We know there is a greater concentration of mass beyond it. We know that if you take the standard interpretation, the arithmetic works. Earth around the sun around the galaxy within its group, the group falling down a density gradient. Add the layers with their directions, and the total is consistent with the observed dipole. And we know that one independent test of that interpretation, counting distant quasars, returns an amplitude about twice as large as the interpretation predicts, at a significance that cannot be dismissed and has not been explained away. Those statements are all simultaneously true, and holding them together without collapsing them into a simpler story is the actual state of knowledge. There is something worth noticing about the aberration effect, the rain and the tilted umbrella, which is that it was not invented for the quasar test. It is 300 years older than that, and the first time anyone saw it, they were looking for something else entirely and were disappointed by what they found. In the 1600s and early 1700s, one measurement mattered more than almost any other in astronomy. If the Earth truly orbits the Sun, then over the course of a year, our viewing position shifts by the full width of that orbit. And if you shift your viewing position, nearby objects should appear to move against a distant background. Hold a finger up and close one eye, then the other, and the finger jumps. That jump is parallax. So nearby stars should show a small annual jump against the more distant ones. Finding it would be direct, physical, unarguable proof that the Earth moves. Many people tried. Everyone failed, and the failure was uncomfortable, because it left an opening for the argument that perhaps the Earth did not move after all. In the 1720s, an English astronomer named James Bradley took up the problem with a collaborator, Samuel Molyneux. They chose a star nearly overhead from London, a star in the constellation Draco, because observing a star at the very top of the sky removes most of the distortion the atmosphere introduces when you look at an angle. To do it, they mounted a telescope vertically in a house, running up through the structure, fixed rigidly, so that the same star crossed the same point night after night. Precision came from refusing to move the instrument at all. They watched, and they found a shift. It was small, but it was real, and it repeated. There was just one problem. It was wrong. Parallax has a specific signature. The apparent displacement of a star should be largest when the Earth is at the extremes of its orbit, at the 2 points where our sideways displacement from the average is greatest. Bradley knew when those moments were. He knew exactly what pattern to expect and when the star should be at its extremes. The star was at its extremes at the wrong times. The whole cycle was shifted by about a quarter of a year, 3 months out of step with what parallax demanded. This is the moment worth sitting with, because it is the moment where a lesser observer stops. He had a real, repeating, unambiguous signal. He could have announced parallax and been celebrated. Instead, he trusted the discrepancy, and the discrepancy told him he had found something he did not recognize. He worked on it for about 2 years without an explanation. The story that has come down to us, and it has the ring of the kind of thing that actually happens, is that the answer arrived while he was on a boat on the Thames. He noticed that the small flag or vane at the masthead shifted its apparent direction each time the boat changed course, even though the wind itself had not changed. The direction the wind appeared to come from depended on the motion of the boat through it. If that works for wind, it works for light. Here is the resolution. Parallax depends on where you are, on your position in the orbit. Aberration depends on which way you are going, on your velocity. And for something moving in a circle, position and velocity are always a quarter cycle out of step. When you are at the far left of a circular path, you are moving directly forward, not left. That is precisely the 3-month offset Bradley had measured. He had not found parallax. He had found the first direct evidence that the Earth is moving, from the tilt in the arriving starlight, exactly as rain tilts for a runner. And there was a bonus, which he recognized immediately. The size of the aberration depends on the ratio between the Earth's speed and the speed of light. He knew roughly how fast the Earth travels in its orbit. So the angle he measured handed him the speed of light, and his value was within a few percent of the modern figure, obtained by watching one star from a fixed tube in a house. Stellar parallax, the thing he was actually looking for, was not measured for another century, because the nearest stars are much further away than anyone had guessed, and the effect is far smaller than aberration. So the same effect that failed to be parallax in 1728, and instead proved that the Earth moves, is the effect now being used on more than 1 million quasars to check whether our motion through the universe is what we think it is. The instrument went from a tube fixed in a chimney to an infrared telescope surveying the entire sky from orbit. The physics did not change at all. There is an objection that should be raised at this point, because if it is not raised, it will sit in the back of the mind and quietly undermine everything. We have said the ancient light gives us a reference to measure our motion against, a universe-filling substance, present everywhere, which we can compare ourselves to. That sounds an enormous amount like the ether, and the ether was disproved. This deserves a straight answer, because the objection is intelligent, and the history behind it is one of the most important episodes in physics. Through the 1800s, the evidence that light is a wave became overwhelming, and every wave anyone had ever studied was a wave in something. Sound is a wave in air. Ripples are waves in water. Remove the medium and the wave cannot exist, which is why a bell ringing inside a jar goes silent as the air is pumped out. So if light is a wave, it seemed unavoidable that space must be filled with a medium for it to wave in. That medium was called the luminiferous ether, and it had to have deeply strange properties. Rigid enough to carry light at enormous speed, yet so insubstantial that planets could sail through it for billions of years without slowing. And it made a prediction. If the ether fills space and the Earth moves through it, then there is an ether wind blowing past us. Light traveling with that wind and light traveling across it should take measurably different times to cover the same distance, in the same way that a swimmer crossing a river and back takes a different time than one swimming upstream and back, even at the same swimming speed. In 1887, Albert Michelson and Edward Morley built an instrument to find it. Their apparatus took a single beam of light and split it in two, sending the halves along perpendicular arms, bouncing them off mirrors, and bringing them back together. When two light waves recombine, they interfere, and the pattern of that interference depends with extraordinary sensitivity on any difference in travel time between the two paths. Then they rotated the whole thing. As the arms swung around relative to the supposed ether wind, the interference pattern should shift. The engineering was remarkable. They mounted the instrument on a heavy stone slab floating in a bath of mercury, so it could be turned smoothly without vibration or flexing, and they folded the light paths with multiple mirrors to lengthen them. They calculated that their setup was sensitive enough to see the expected effect several times over. They turned it. Nothing happened. They repeated the experiment at different times of day, catching different orientations as the Earth rotated. They repeated it at different times of year, catching different directions as the Earth moved around the Sun. If the Earth had happened to be momentarily at rest with respect to the ether, 6 months later, it would be moving through it at double speed, and the effect would be unmissable. Nothing, ever. It is the most consequential null result in the history of physics, and it broke the ether. Various rescue attempts were proposed, some quite ingenious, but the situation was finally resolved by discarding the medium entirely. Light does not need something to wave in. Its speed in empty space is the same for every observer, regardless of how that observer is moving, and building physics on that fact is what produced relativity. So, is the ancient light just the ether wearing a different name? No, and the difference is precise rather than a matter of taste. The ether was proposed as the medium light travels in. Its whole point was that your motion with respect to it would change the speed at which you measure light to travel. That is the claim Michelson and Morley tested, and that is the claim that failed. The ancient light is not a medium for light. It is light. It is a very large number of actual photons flying through space, and moving through them does not change the speed at which any light beam travels. Set up the Michelson and Morley experiment today, in a laboratory saturated by this ancient light, exactly as every laboratory is, and you will get the same null result they did. The speed of light is unaffected. What changes when you move is only how many of those particular photons arrive from each direction, and with how much energy. The distinction is between a medium that governs the laws and a substance that happens to be lying around. The ether was supposed to be the first. The ancient light is the second. Measuring your motion with respect to it is no more mysterious and no more of a threat to relativity than measuring your motion with respect to a passing cloud of dust. The cloud is simply much larger and much older, and everyone has one. Now, what does all this motion actually amount to? Take the figure we have been carrying, roughly 370 kilometers per second, and run it over a human life. Across 80 years, that comes to something like 900 billion kilometers, which sounds like an enormous distance, and it is. But the universe is a difficult place to feel impressed in. 900 billion kilometers is about a tenth of a single light year. The nearest star system to our own sits a bit over 4 light years away. So over an entire human lifetime, at a speed that beats every spacecraft ever built, you cover roughly a 40th of the distance to the nearest neighboring star. You are moving extraordinarily fast through a space that is extraordinarily large, and the largeness wins by a margin that does not really shrink. But some of these motions do arrive somewhere. Andromeda, the nearest large galaxy to our own, is not receding. It is approaching at somewhere around 100 kilometers per second. This is one of the few large galaxies with a blue shift rather than a red shift, because within a gravitationally bound group like ours, gravity has already won against the expansion. The local group is not expanding internally, it is falling together. Current modeling suggests the Milky Way and Andromeda will begin seriously interacting in something like 4 to 5 billion years. And the word collision, which gets used constantly, is misleading in a specific way that is worth correcting. Stars will almost certainly not hit each other. The spacing between stars inside a galaxy is so vast relative to the size of stars that two galaxies can pass through one another with essentially no stellar impacts at all. What will happen is that the gas clouds will collide, because gas fills space in a way stars do not, and the two structures will be pulled apart and rearranged by each other's gravity over hundreds of millions of years, eventually settling into a single, larger galaxy. It is worth adding that the confidence around this has softened somewhat in recent years. The outcome depends on the sideways component of Andromeda's motion, which is far harder to measure than the component along our line of sight, and improved measurements have widened rather than narrowed the range of possibilities. A merger remains the most likely outcome. A near miss followed by a later merger or a longer delay is not excluded. This is a case where more precise data made the prediction less certain rather than more, which happens more often in science than the popular account suggests. And then the larger flow, the one toward the Great Attractor region and the Shapley concentration, has a different ending. We are falling toward it. We will not arrive. The expansion of the universe is accelerating, and that acceleration works against the assembly of any structure that is not already gravitationally bound. Our local group is bound and will stay together. Laniakea is not. The flow we measure is real, and the pull is real, but over the timescales required to actually converge, the expansion will have carried those regions away from each other faster than gravity can draw them in. So the map we drew, the immense heaven, the watershed defined by which way everything is flowing, is a snapshot of a pattern in the process of being erased. The galaxies of Laniakea are like leaves being drawn toward a swirl in a river that is itself widening faster than the swirl can gather them. The motion is genuine. The destination is not reachable, which brings us back to the question we started with, and to what the answer actually is. Ask which way you are moving, and the honest reply is another question. With respect to what? With respect to the ground, you are still. With respect to the center of the earth, you are turning at a speed that depends on your latitude. With respect to the sun, you are traveling at about 30 kilometers per second in a direction that reverses over the year. With respect to the center of the galaxy, you are moving at roughly 230 kilometers per second on a circuit that takes hundreds of millions of years. With respect to the other galaxies of the local group, you barely move at all because you belong to that group and travel with it. And with respect to the oldest light in the universe, you are moving at roughly 370 kilometers per second toward the constellation Leo. Every one of those answers is correct. None of them is more true than the others. What relativity forbids is not answering the question. What it forbids is answering it without naming the reference. And that is the quiet resolution of the paradox that has been sitting under this entire story. The warm patch in the sky does not give us absolute motion, and it never did. It gives us something more modest and, in practice, more useful. It gives us a reference that everyone in the universe has access to. Any observer anywhere, in any galaxy, at any point in the last several billion years, can look at their sky, find the ancient light, measure its dipole, and determine their velocity with respect to it. They do not need to know about us. They do not need a shared landmark or an agreed origin. The reference is delivered to them, filling their sky for free. That is not a preferred frame in the sense that physics forbids. The laws work identically for someone at rest with respect to that light, and for someone moving through it at half the speed of light. Nothing about the physics singles it out. What singles it out is availability. It is the one thing everyone can see. The universe did not give us an absolute answer. It gave us a common one. Before drawing this together, there is one practical question that has been skipped, and a careful viewer will have noticed the gap. We have talked throughout about measuring the temperature of the sky in every direction, as though you simply point an instrument and read a number. You cannot. Because the microwave sky is not only filled with ancient light, it is also filled with our own galaxy. The Milky Way glows in microwaves through at least 3 separate mechanisms. Electrons spiraling along the galaxy's magnetic fields radiate as they turn. Hot ionized gas radiates as free electrons pass near ions and are deflected. And cold dust grains, warmed slightly by starlight, radiate a faint thermal glow. All 3 produce microwaves. All 3 are strongest along the plane of the galaxy, which is to say, exactly where the curtain is. In places, this local glow is not a small contamination. It is far brighter than the 1 part in 1,000 asymmetry we are trying to measure. Reading the raw microwave sky and calling it the ancient light would be like trying to measure a distant lighthouse while standing next to a bonfire. So how do you take the bonfire out? You use the fact that different sources of light have different characteristic shapes across the spectrum. The glow from spiraling electrons is strongest at low frequencies and falls away as you go higher. The glow from cold dust does the opposite, rising steeply toward higher frequencies. And the ancient light has an extremely specific spectral shape, the shape produced by any object in thermal equilibrium, and crucially, that shape is identical everywhere on the sky. Only its overall level shifts slightly. So instead of observing at one frequency, you observe at many. The most detailed mission of this kind surveyed the sky in 9 separate frequency bands, deliberately chosen to straddle the region where the ancient light dominates, and to reach out on both sides into territory where the galactic sources take over. Then, for every point on the sky, you have 9 numbers instead of 1, and you ask which combination of known spectral shapes, added together, would produce those 9 numbers. If you have ever listened to a recording of several instruments playing at once and been able to follow the cello, you have done a version of this. The sound arrived as a single pressure wave. You separated it because each instrument has a characteristic tone, and your hearing knows those tones well enough to pull them apart. Component separation in cosmology is the same operation performed deliberately and with arithmetic. The dipole is, in one respect, an easier target than the fine-grained structure cosmologists usually care about, because it is an enormous smooth pattern spanning the whole sky, and the galaxy is not smooth. A narrow bright band and a broad gentle gradient look very different, but the risk is real. Because if any of the galactic emission is modeled slightly wrongly, in a way that varies smoothly from one side of the sky to the other, that error leaks directly into the thing you are measuring, which is why the annual wobble matters so much more than it first appeared. Recall that the Earth's orbit contributes its own piece to the dipole, and that piece reverses over the course of a year. We know the Earth's orbital speed with extraordinary precision, so the dipole is required to shift by a specific amount, in a specific direction, on a specific schedule, every year, forever. The galaxy does not do that. Our galaxy's emission does not vary annually. Dust does not brighten in March and dim in September. So the annual modulation gives an internal check that no amount of foreground error can imitate. If your extracted dipole wobbles by exactly the predicted amount on exactly the right schedule, then whatever else may be uncertain, the instrument is measuring motion and measuring it correctly. That signal has been detected, and it behaves as it should. That is the difference between a measurement you believe and a number you merely computed. It is worth putting the whole chain in plain terms, because a great deal has been assembled, and the argument is easy to lose inside its own detail. The oldest light in the universe fills the sky in every direction at almost exactly the same temperature. One side is very slightly warmer than the other, by about 1,000th of the total. Motion produces exactly that pattern, because moving toward light crowds its waves and raises its energy, and moving away stretches them. So the warm side tells us which way we are going, and the size of the warmth tells us how fast. We then took that single combined number apart, layer by layer, using motions we can check independently. The Earth's orbit contributes a piece that reverses over the year. And it does reverse, exactly on schedule, which tells us the measurement is sound. The Sun's orbit around the galaxy contributes a much larger piece in a direction fixed by the geometry of the Milky Way. What remains after removing those is the motion of our whole local family of galaxies, and it is larger than either. To explain that remainder, we measured other galaxies, thousands of them, working out how far away each one is from its own internal motions, then comparing the recession we expected from expansion with the recession we observed. The gap between the two is each galaxy's own motion through space. Mapping those gaps across the sky gave a flow, and the flow converges toward a region hidden behind the dust of our own galaxy, which we eventually surveyed using wavelengths dust does not block. Beyond it lies a still greater concentration of mass. Then, as a check, we counted more than 1 million distant quasars, because our motion should crowd them slightly toward the direction we are heading and brighten them slightly as well. The direction of that imbalance matched. The size did not. It came out about twice as large as our motion should produce, and that discrepancy has resisted several years of attempts to explain it away. That is the state of the question. Now, what would actually settle it? Several things are arriving, and this is one of those situations where the resolution is genuinely on the calendar rather than indefinitely deferred. The core weakness of the quasar test is sample size and uniformity of coverage. A dipole is a large-scale pattern, and to measure it cleanly, you need a catalog that covers the entire sky with consistent sensitivity, which is exactly the thing that is hard to build. New radio surveys with far greater depth are mapping the sky with instruments designed from the start with this kind of measurement in mind. New optical surveys will catalog an enormous number of galaxies and quasars with well-characterized selection. Larger samples reduce the statistical noise, and better understood selection reduces the systematic risk, which are the two things standing between this result and a verdict. There is also a second front, which is testing the same question with entirely different objects. If the excess is real and cosmological, it should appear in other populations too, at a size that can be predicted. If it appears only in one kind of source, that points towards something about that population rather than about the universe. Work along these lines has already begun, with supernovae and with galaxy clusters. And the results so far have been suggestive rather than decisive, partly because those samples are much smaller. And there is a third avenue that is more subtle and more elegant. Aberration does not only shift the positions of distant sources, it also very slightly distorts the fine-grained pattern of the ancient light itself, mixing its features together in a way that depends on velocity. That effect has been detected, and it offers a way of measuring our motion from the ancient light that is largely independent of the dipole. Early measurements of this kind have been broadly consistent with the standard interpretation, though with substantial uncertainty. Sharpening that measurement would provide a genuinely internal check, so within a reasonable span of years, this will most likely be one of three things: a systematic that got understood, a property of quasar populations that got modeled properly, or a real feature of the universe that requires the foundations to be revisited. Any of those three outcomes teaches us something. That is a comfortable position for a science to be in, and it is worth saying plainly, because the version of this story that travels furthest is usually the one claiming that cosmology is in crisis. A measurement that disagrees with a prediction is not a crisis. It is the mechanism by which the field finds out what it got wrong, and it only works if people take the disagreement seriously rather than smoothing it over. There is one more limit worth acknowledging, and it is the oldest one in this story. We still live inside the Milky Way. The zone of avoidance is smaller than it was, because infrared and radio and X-ray observations have pushed into it, but it has not gone away. There remain regions behind the densest parts of our own galactic plane where our census of what lies beyond is genuinely incomplete. And it happens, awkwardly, that the direction of our motion passes close to that plane. So part of the reason the flow story took so long to assemble, and part of the reason some analyses have found a residual they could not account for, is simply that a fraction of the relevant sky is difficult to inventory from where we are sitting. There is no clever fix for this. We cannot leave the galaxy. We can only keep finding wavelengths that pass through it, and keep improving how we infer what the masked regions contain. Which means the answer to a question about our own motion is limited, in part, by our own position. Not as a matter of principle, but as a matter of geography. Now, step back from all of it. You started this by sitting still, and the claim was that you were nonetheless moving at 370 kilometers per second toward the constellation Leo. That claim survives. It is well measured, and the mechanism behind it is understood in detail. What has changed is what the claim means. It does not mean you have a true velocity that the universe secretly knows. There is no such quantity. Every attempt to find one has failed, and the failure is not a gap in our knowledge, but a feature of how motion actually works. Galileo's cabin below deck is still sealed, and no experiment inside it will ever tell you whether the ship is underway. What it means is that the universe happens to contain a substance which fills all of space, arrived from the same era everywhere, and can be seen from anywhere. Our relationship to that substance is measurable. And when we measure it, we discover that we are not drifting randomly. We are being pulled, along with everything nearby, down a gradient in the distribution of matter that was laid down when the universe was young. So the direction you would point, if you raised your arm toward Leo, is not arbitrary. It is the direction of the largest concentration of mass whose gravity has had a meaningful grip on this corner of the universe. Your body is participating in a fall that began before the sun existed, that includes every star you can see, and that will still be happening long after the Earth is gone. And it is recorded. That is the part that keeps being remarkable no matter how carefully you take it apart. The oldest light there is, released when the universe first became transparent, before any star had formed, carries a faint asymmetry across the sky. And that asymmetry is not about the early universe at all. It is about us. It is the mark our motion leaves as we move through the light. Every observer sees a different warm side in a different direction according to their own travel. The light is the same. The lopsidedness belongs to the observer, which means that anyone, anywhere, at any time, who is patient enough and careful enough to measure the temperature of their sky in every direction will be handed their own velocity by the universe itself without asking for it. We know which way we are moving. We know it because a hiss that two radio astronomers spent months trying to eliminate turned out to be the beginning of everything, and because a satellite measured differences instead of totals, and because a man in the 1720s trusted a discrepancy of 3 months instead of publishing the result he wanted. We know how fast. We know most of what is pulling. We know where the curtain is that still hides part of the answer. And we have one measurement made by counting more than 1 million distant objects, which says our number may be wrong by a factor of 2, and which nobody has yet been able to dismiss or confirm. That is not a failure of the account. It is the account. The sky has a warm side, we know why, and we are still checking.